Good evening, everyone. We're going to talk about LED maintenance factor tonight. I'm James Lescu here. I'm with GHD. We're talking about some stuff that I've developed in my own time at work that I just recognised there was some gaps in how we as an industry used maintenance factor, particularly with LED more than anything else. And so I just took the time to start doing my own thing, as it were. Today we're going to sort of go through the standards, the old 1680.4, which was written in 2001, obviously before LED, and the one that was released this year in 2017. Did everyone read 2017? Is everyone fascinated and know exactly what it says and all the important information from that? Big hands of none there. But I'm just going to talk about how I interpret that standard as well, which is an interesting one, and sort of this tool that I've developed and how I actually started developing this tool prior to the standard coming out, and the standard coming out sort of just prompted me that it was a valuable tool, because you'll find out why soon enough. I obviously need to go through the basics of maintenance factor. Certainly some of the older gentlemen in the room are going to know maintenance factor through and through. Some of the younger gentlemen who haven't done the course, possibly not. Maintenance factor consists of 4 key components. You've got your luminaire maintenance factor, lamp survival factor, room surface maintenance factor, and lamp lumen maintenance factor. Whack them all together and gives you a holistic maintenance factor for a luminaire within a room. It does relate to a room as much as anything else, not how you install a luminaire changes that maintenance factor. A maintenance factor isn't per luminaire, it's per luminaire plus installation. LMF is basically how the dirt or the environment affects the luminaire. It consists of a temporary component, and that's like dust on the lamp itself, which can be wiped off quite simply, whereas a permanent component might be pitting of an optical surface, and that is a permanent degradation of the luminaire source. There's the lamp survival factor. That's just how many lamps have been turned off due to failures, lamp blowing, that sort of thing. Spot replacement means it's gone out, we've immediately ripped it out and put in a new one, whereas a frequency replacement might be every year when we come out to do maintenance. Generally, that's when we look at the failures and we replace them at that time. Room surface maintenance factor, it's the degradation due to room conditions, whether that be just the room getting old and the walls getting dirty, or just how we install it, whether we have a very tall, narrow room that the light needs to bounce off a lot of walls to get down to the floor, or whether we have a flatter sort of room, and that's all part of the room index. And our major talking point for today is actually the lamp lumen maintenance factor, and this is the life of the lamp source. And it's often incorrectly used as the only characteristic in maintenance factor calculations. This is the one that people say, oh, the luminaire lasts this long, hence I'll give it a factor of this. The other 3 are casually ignored most of the time, incorrectly. And these 4 are directly all from the standards. All from, well, as far back as 2001, and probably older. I haven't gone back that older. I've been designing since somewhere after 2001. So I'm not, hopefully none of the information was brand new to you, generally. You've all hopefully read this standard at some point, and you're all generally on top of that 4 basics of maintenance factor. Let's get into an example of how that comes together in a lighting installation using a traditional source, a fluorescent source. And this is generally the scenario we're going to run throughout the day with today, except in one case. We're going to run through an open office fit out. It's nice and simple. We all understand how they look, with a 25 by 50, 3 metre brand new office in the city, 3 yearly cleaning. Later we'll change to a yearly cleaning. In this case, we'll use a 3-year design life for those lamps. We'll expect our long life T5 lamps to get 3 years. An IP2X direct luminaire, I'm sort of thinking like the Future 5, if you all know that old fitting. I've got them in my office. They look great. We're going to compare, it's a louvered fitting if no one's familiar with it. We're going to compare spot replacement versus the frequency replacement and see what happens from that. Just for our own information, hours are important on how long we run things. If we take 13 hours a day, being in a typical office is what I find, our office runs at about 13 hours a day when people get in early and leave late. For 5 days a week, 52 weeks in a year, 3 years, gives us about 10,000 hours. We'll work with that for the time being. We'll change it later, try some different numbers. So 10,000 hours, in case you wonder where that comes from. I got sick of opening the standard all the time and reading the tables and grabbing a number and writing it down on a piece of paper, turning to the next table, grabbing the thing, doing the number, next table, etc., etc. And I'd end up with 4 numbers that I'd then multiply to get an overall maintenance factor. This seemed like a bit of a time-consuming thing for me, so I developed a tool that directly related to 1680.4. It's got, in the back end, all those tables directly into it, just uses a lookup, nothing advanced as far as a Excel tool. And actually includes a little bit of text saying assumption. You'll see it. It's a little bit of assumptions text, helps us get through the deal and heads into it. Let's have a look at that tool, and we'll call this example 1 incomplete, because we're going to fill it in together using those numbers I just did. And we're going to hide all that today. We don't need any of that. Luminaire type, as we discussed, is a enclosed fitting. Atmosphere, clean, brand new office. Interval, we looked at 3 years worth of cleaning. As you can see, I've assumptions to include in the report, nice and simple things. Lamp type, we've got our long life T5, operating for 10,000 hours, using let's try a frequency replacement to start with. Distribution is of course a direct fitting, mounted at 3 meters, and the room was 25 by 50. There we go. LMF, LLMF, LSF, and RSFMF are multiplied together to give us our overall maintenance factor. And then we can change that to spot, and it changes our maintenance factor. Nice and simple. Actually, I want to close that, otherwise I'm just going to end up with tons of Excel sheets. There's our numbers and our other one, and here's the two compared. You can see that our maintenance factor is between 0.72 and 0.67, depending on whether we use spot replacement, frequency replacement. Our LSF is really the thing that changes. Our LMF and our RSMF, and I'm going to get sick of saying them all night, stay exactly the same. You see that between 0.72 and 0.67, using this very typical fit out, we're all very familiar with how an open office would look, and those numbers were nothing extravagant. Hey, that's about the 0.7 that a lot of people quote when they talk about fluorescence, right there. Let's talk quickly about where this LLMF figure comes from. That's why I've highlighted it. And that's from the 2001 standard. That's this table here, where we take our lamp source, being a long life fluorescent, and our operating hours being 10,000 hours, two together, down the table, there's our LLMF. This is actually 2 tables combined in one. There's the LSF there too. That's where that 0.93 came from. But topic of today is mostly around that LLMF. Just keep in mind that we do have 3 other factors that do affect our lamp life and luminaire life. Hopefully this is nice and easy. The notes down the bottom just says check with the lamp manufacturer, get your own data, but generally this is okay. Let's talk about the guts of it, the LED stuff. LED was obviously not represented in that standard. There was a lot of interesting sources there, some that possibly no one's really planning on using anymore, but they're still there because we still need to consider them. Without any direction on LED, we sort of led to making a bunch of assumptions as an industry. One of them is that LEDs, hundreds of thousands of hours. We don't need to think about this. It's got a life we don't need to worry about. Why would we think about life? It's just better than the traditional sources, and we need a better maintenance factor to represent that betterness. We recognise there are failures with LED. It's not a perfect source, and 0.9 is not an ideal number. So we just made up a number as an industry, and that number was 0.8. And we're all sitting there nodding, and we all know that 0.8 is just a number that we invented. That's the number. Premium manufacturers tend to give us a nicer number. They said, 0.85 or 0.9. I've seen even higher. Phil brought me some data today. They're saying 0.99. You know, that's interesting stuff, because they're trying to set their product apart from others. And this is how they can say, we sell quality LED chips compared to theirs that don't. And that's part of the failures of the assumption that we're comparing old LEDs versus new LEDs with maintenance factor, but we're also comparing good LED chips with bad LED chips. And all this data that we're being thrown, this 0.8 and 0.99, that's still just the LMF data, but we keep sticking it in as our holistic maintenance factor. When a manufacturer says 50,000 hours, 58,000 hours to what? And that's where we started to develop this new representation of data, where we talk about an L value and a B value, L being the depreciation curve over time, and B being the factor of those luminaires along that depreciation curve. I'm hoping that makes sense. It's not everyone quotes the B value, but it's definitely something I like to request and ask for.
So what's the B10? You've got the 100,000 hours L90 B10.
Yes, so how do you compare those three fittings from an LED? Because they're all an LED source. Yeah, so that's what we're going to get into today is how we compare those three. But B10 means about 10% of those fittings have reached L90 at 100,000 hours, as opposed to L70, B50, 50,000 hours says about 50% of those LED fittings have hit L70 at 50,000 hours. So you can see straight away that an L90, B10, 100,000 hours fitting is better than an L70, B50, 50,000 hours fitting. But how do you compare those two, considering that's your end point? And you know your start point, but you know nothing in the middle. I'm just going to simplify some factors as well. Life consists of two parts, and this is where I'm getting into this, what's the middle point? Life consists of two parts. It consists of the desired life, how long you want it to live, and how long it's rated to live. And the two can go either direction. You can expect something to live longer than how long it's rated for. But because it's just hours, we can combine it in a single ratio. It gets rid of the hours bit, it just turns into a percentage. Because a maintenance factor is a unitless number, hence it either needs to cancel out within our calculation or it needs to cancel out at the start. I'm just cancelling it out at the start. What's changed in the lamp lumen maintenance factor between a traditional source and a modern source? And this is how I've interpreted it. Some other people might interpret things slightly differently, but this is how I've seen the differences in maintenance factor, lamp lumen maintenance factor over time. And a key component of that is that previously a fluorescent lamp was a very known source. There were really only 2 or 3 names that made a fluorescent lamp, and they're all exactly the same as far as their lamp life. Their rated life could then be published directly in a standard as far as numbers over time. You could put in hours and this would be about the lamp lumen maintenance factor you'd get, and that's why we saw that in the standard. Whereas with an LED, we're going to see the rated life not just by LED chip, but by the manufacturer who sticks it in that luminaire. The same chip in 2 different luminaires can perform completely differently. And so that traditional thing, we can use the manufacturer data. It's all fixed curves. It's very easy to understand. Whereas this modern stuff, because it's so new, no manufacturer even has curves. And if they do have curves, I generally haven't seen them. So our previous LMF inputs were just the rated life, desired life, that factor, plus the lamp type. Very easy to calculate. Whereas our new LLMF, we've got this life factor, as well as our L value and our B value. And we've turned from having a 2-variable solution, something that was very easy to understand with a simple input-output, something that worked well in a table, to a 3-variable solution. And once you start talking your lamp life, and, sorry, not your lamp life, your rated and versus desired life, and your L value and your B value, you're ending up with a 3D cube table. And it's very hard to represent on a piece of paper, this understanding of lamp life. And so where there was previously a single curve for a source, a fluorescent source, very easy to track, our LED sources have many, many curves per fitting typically, not even per hours or rating, that sort of thing. It comes down to the manufacturer and how well they build it. So with our 3 variables, we have new problems. The tables just don't represent a 3-variable issue very well, and the engineers in the room will understand why. It's because there's only 2 sides to a table. The 2001 standard represented the data by lamp source, whereas there's additional data within an LED source. It's variable within itself. The best representation of the data was too complex for such a simple problem. Like, maintenance factor is ultimately a tiny bit of what we do. It's such a simple problem. And no one's really applied too much thought to this thing. So as a result, we've just used 0.8 because it'll be okay overall. Day one, the client's not going to complain because it's going to be too bright. And it's really down to 2, 3, 4, 5, 10 years when we start to have problems, and then it's someone else's problem, right? Right. That's why we use 0.8. So the correct application of LED, LLMF, still requires a formula, not a table, a formula with 3 inputs and 1 output. And thankfully, the 2017 standard intends to fix that. It actually addresses LED sources. Here's our standard, our new 2017 standard. And since it looks like no one's read it today, I've actually summarised it for you. There's 2 changes. Cleaning stuff. Vague cleaning is now removed generally. And there's some LED stuff. That's the standard in a nutshell. That's how I summarise it with 4 words. We have a new table at the back, 2017 standard. And look, LED. This is fantastic. We're finally starting to talk about LED. But we've still got a problem. There's still only 2 variables. And those variables aren't even the ones I was talking about. We're still talking lamp type and lamp operating time. That's interesting. And it only goes to 24,000 hours. That's an interesting point to stop LED. But then we'd start going into multiple pages, perhaps. I'm not sure. But thankfully, there's some data down the bottom that clarifies it. And I've summarised that for us today. Point 1 is get your own data. Point number 2 is if it's really small, use 1. Otherwise, get your own data. And point number 3 is get your own data. So it's really just solve the problem of LED by telling it's your problem, which hasn't solved any problem, has it? Because that's what we had previously. We were previously told to get our own data because we had no information, and as a result, we used 0.8. So this new standard has addressed the problem of maintenance factor for LED by telling us that what you're doing is whatever. That's the response I get out of that. Congratulations, whatever. So the failings of the new standard, the LED data, I don't know if you actually read that data there. I just found it completely irrelevant. Like 0.88 at 24,000 hours, is that a good source? Is that a bad source? Generally, it's a bad source. That's how I see it. Maybe it's just to make it so only the bad LEDs get applied to that, and when you get your own data, you only apply it to the good LEDs. But it still uses the same 2-variable table to a 3-variable problem, and it doesn't use the same 3 variables that I've identified are required. In the vast majority of cases, it's just telling you to talk to manufacturers, and the manufacturers don't have that data either. They know where it finishes. Our finish point is L70, B50, 50,000 hours, or L90, B10, 100,000 hours, whatever it might be. They might have that curve in the middle. I don't know. I haven't really seen much of it published. And that rated life, that L70, B50, 50,000 hours, doesn't really help me to determine what's happening in the middle between your start point, where you're at L100, at 0 hours. How do we get to the L70? And certainly that table didn't help with LSF. It just said 1 in all cases, and then it got to a point where it said, talk to the manufacturer. And that's actually an F value. That's a whole different thing, and I haven't even addressed that. So if I haven't addressed it and the standard hasn't addressed it, we're all still in the dark. And that standard was, of course, obviously limited only 24,000 hours, and I haven't seen many LEDs published at less than 30,000 hours. So I developed this tool, and it was all developed pre-2017, and it hasn't taken anything from 2017 standard into account yet. That's probably the next update, is to take that note 2 where it says LLMF is 1, less than 50% of its rated life. Probably implement that into it. But it's ultimately a tool that I originally started doing for traditional sources, and then I said, well, maybe I can apply this to LED sources, and I originally calculated LED sources and output a reasonable LLMF at every point in its life. And I spent a lot of time tapping into a calculator. It's good fun. And then I made my own table to look up, and using my lookup tables. And there was several tables, multiple tables, depending on the data you could stick into it. And it became quite cumbersome to update. So I now changed to a formulaic calculation method. There's a formula at the back end, and I'm pretty impressed at how it works sometimes, because I'm still scratching my head. I'm not saying it's perfect, but it's certainly a lot better than the standard as far as how I read it. It also forces you to use all the maintenance factor components to create a holistic maintenance factor. It's not just going to spit you out an LLMF. It'll only give you the final maintenance factor once you've entered all the data, which you've probably noticed on the earlier example there. And other than LLMF, it follows 1680.4 precisely. So I've just created my own way of doing LLMF for LEDs. That's all I've done. Obviously not LSF, like I was saying, but both the standard and me are pretty silent on LEDs for that. And I actually, being a formula, I can just turn it into a chart. So turned into a chart because charts look nice. I hope you guys weren't expecting many pictures today. This is mostly text and me talking. Let's go with an example. This is the example where we're departing from the open office, but let's talk about a fancy bathroom. It's quite a small one. It's brand new, but we give it a huge clean every Christmas break. It gets its daily clean, please, but it also gets a big clean over the Christmas break. Let's give it 10-year design life. Yeah, and with that being an LED fitting, let's expect it to last 10 years, because it's only a fit out for a corporate executive at the back of the whatever it might be. Sure. It's got a little motion detector, gives us occupancy detection. So 13 hours a day, 5 days a week, 52 weeks, 10 years and 0.25% occupancy. We get 8450. Let's get a nice fitting with IP5X from below, and we've spent the big dollars on an L90 B10 100,000 hour fitting. We're not expecting it to die, but if it does, we'll get the guy out to replace it. Probably the fitting of that thing, we're talking 5-10 year warranty anyway, so it's covered under warranty, let's say. But you can see I've absolutely put the most stupid fitting as far as overkill into what's ultimately a stupid problem. But it's worth having a look at how that turns out with the maintenance factor. So let's get into the example there. All right, our quality LED downlight is a dustproof fitting. Its atmosphere is clean. I've got little notes over here as well. They really help out as far as reading what's going on. And these are text, I believe, that are straight from the standard or otherwise clarified by me. Interval, we were cleaning it yearly. Its L value was L90, B10, 100,000 hours. There's enough zeros. And we've got 8450 on its life. Its distribution was direct. Its mounting height is 3 meters, and it was a 3 by 5 meter bathroom. Hey, there's a maintenance factor, 0.9. We all like that one. And there's a nice chart there as well. So that's how the tool works, as simple as that is. We actually want to close that. It's not particularly complex by any means. It sort of forces you through it and gives you that as a result. And a chart, pretty chart. We've got our planned life up to 100,000 hours, and then after that point, I assume they start dying more frequently or degrading in lumen output more frequently. It's more of a visualization as to how the data is working than anything else, making sure that it is making sense. But let's really get into the interesting ones where we compare a fluorescent versus an LED. An open office fit out, just like our old one, 3-year cleaning. The fluorescents, we get a maintenance contract out. We're expecting them to last 3 years. Every 3 years they walk through, give the luminaire a wipe down, give the lamp a wipe down, replace the ones that have failed. Whereas an LED, they just give it a clean down every 3 years, and otherwise the fit out's only supposed to last 10 years. So this one's only getting 10,000 hours per lamp, whereas when we start multiplying this one out, we're expecting to get 34,000 kilo hours out of this fitting. Still less than our L70 B50, 50,000 hours. It's not unreasonable. And we've got our 2 lamp sources there, long life T5 and an LED. This is a very typical comparison. You know, everyone's nodding their head there. It's nothing special. Has anyone got any predictions? Anyone want to predict which one's going to pull out on top there? Let's grab that in there. Sample 3. So here's our traditional source. Nothing special there, but we worked it out as a 0.82 fluorescent source. It's not bad. It's pretty good. Very good, even. It's probably helps the most that we've got a long life in there rather than just a standard T5, but most, the cost difference between a long life and a regular T5 now doesn't really make too much difference. If you're curious, I'll just swap that over. Hasn't really changed much, 0.72. How about that LED? Oh, how about that number? That's a very different number. That's saying our L70 B50 50,000 hour LED is worse than a long life fluorescent. Yeah, all right, let's have a little bit more of a discussion about that one. There's the data compared right next to each other. There's nothing special. They're both LMF 0.88, RSMF 0.98, still being installed in the same room, in the same way. LSF in both cases is 1. We're just going to replace them as they die. Our LLMF is where we're showing the difference. Hey, look, 0.8. Anyone heard of 0.8 before for LEDs? Here it is right here. 0.8 for an LED is an LLMF figure for an L70 B10 50,000 hour luminaire at 34,000 hours point of its life, 10-year usage. That's interesting. As I mentioned, a standard T5, not long life, is still beating our LED. Let's improve things. Let's make this LED better. Let's use the quality fitting. L90 B10 100,000 hours. That's the only change. We've upgraded from an L70 B50 50,000 to an L90 B10 100,000. We've paid a lot more for the fitting, and it's going to have that European feel. We'll appreciate that. And here's the difference there. I've got the calc there if you want to have a look at it here and we can fill it in together, but you're taking my word on it that those are the... You're going to trust me? Beautiful. Finally, when we compare our L70 B50 50,000 hours to our L90 B10 100,000, now we are beating that fluorescent T5 long life fitting with a decent quality LED luminaire. That's the only difference, is just improving the quality of the luminaire. Can we get to 0.9? Anyone reckon we can get to 0.9? I'm pretty excited to get to 0.9. We can do that through a really simple change. If you noticed the products earlier with our fitting, it's really easy to pick how to improve that, and that's by changing from an IP2X luminaire to an IP5X. A lot of manufacturers have IP4X, and I go, well, actually, that's not an IP5X, so we're going to have to keep using the 2X numbers, because the 5X will make a huge difference to our calculations. And again, comparing things, we've got our LMF at 0.88, which is what was bringing down all previous calculations with an enclosed IP2X fitting. When we change it to a dust-proof fitting, our LMF jumps up to 0.94. And 0.94 times 0.97 times 1 times 0.98 gives us pretty darn close to 0.9. So you can get a 0.9 maintenance factor, holistic maintenance factor of 0.9 with an LED luminaire, with a quality luminaire in a clean, dust-proof environment. It's certainly possible. And that downlight we had that was overkill in that bathroom earlier, that certainly was beyond 0.9. So we need to consider that it's really important to factor in this total life of a luminaire more than anything else. How long is this luminaire expected to stay in service? Don't just get the L70 B50 50,000 hours or the 100,000 hours, whatever it might be, and say it'll last forever. How long is it actually expected to last? This is really important to me because Defence MIEE, if you've read that standard, says all electrical equipment will will run at 24/7 at the extremes of heat and temperature and humidity for 50 years without the need for excessive maintenance. That's how it reads, which we all can agree is stupid because I don't expect a light switch to do that, but we're still sticking light switches. So consider how long you want something to exist within the fit out. A 10-year fit out is the standard rollover in a commercial building, that's a good number to use. Even if they do a refresh every 5 years, they're generally not going to do the lighting. They're just going to change the furniture and give it a polish. So the 0.8 maintenance factor holistically can be okay under the right conditions if you've assessed it. Today I've proved that you can get from under 0.7 all the way up to 0.9 in a standard office fit out, purely based on the luminaire that you use, not changing spacing or anything like that, or room conditions. It can be quite variable. It's generally closer towards the 0.7 side of things than it is closer to the 0.9 side of things. And those quality luminaires do make a significant difference to the results. That's where I'm getting at that, you're spending money for this fitting. You really are. Let's be practical. You spend a lot more for it, but the greater maintenance factor means you can space it out more. Overall, it's up to the engineer to assess whether that L70, B50, 50,000 hours fitting is most appropriate, or whether you want the 100,000 hour fitting and have a great spacing. The capital may be the same or less or more, depending on your exact circumstance. It's also important to consider build quality. I like getting luminaires in hand and twisting them and turning them and seeing if the sheet metal bends or warps, or looking at the LED board and seeing how it's soldered together and seeing if the flux is splattered everywhere or whether it's actually been done properly. It's really something, a lot of people just go, yeah, it's a luminaire. I like looking at those luminaires to see how they turn out. So all this previous data, it has to assume that they operate at suboptimal conditions. That's the data you get from the manufacturer. They say that this is the L70, B50, 50,000 hours when it's operated at 40 degrees on a humid day. That's the data they give you. It's not being operated in that condition. It's being dimmed because it's required under J6, or it's a nice air-conditioned space and it's got 21 degrees. So there's plenty of cases where that LED is doing a lot better. So if you can justify using your own numbers, if you can justify that it's going to get better than that, that's up to you. At the moment, there's no easy way of changing the temperature and as a result changing the life of an LED. I don't have a fix-all for that yet. So a little bit of a summary. 1680 didn't have LED at all. So the industry fabricated an unchanging and an incorrect value. It's 0.8, that was this fabricated number that we made, and it was a LLMF figure that we used as a total maintenance factor figure, is how I read it. So a new standard came out, and it still has its shortcomings. It's taken a 3-variable problem and whacked it into a table, and the table's not quite working yet. And in the vast majority of cases, it's just saying talk to the manufacturers. So let's talk to the manufacturer, and I'm happy to talk to any of the manufacturers here today, and none of them are going to have curves. None of them have it. It's unknown or it's unpublished. There's a hand. Yes?
I have curves for every luminaire I sell.
Beautiful. Someone has curves for every luminaire he sells. That's a step up from what I've seen so far. So I developed a tool. It occurred pre-2017 standard. So I didn't know what the 2017 was going to say, but it creates a total maintenance factor. It's not a perfect tool. I know its shortcomings, but it accounts for the manufacturer data as it's provided to me. Being I can compare, when everyone gives me a 100,000 hour L90 B10 fitting, I can compare them all, or whatever ratings they give me, I can compare them all equally. While one person has curves, not everyone has curves, and then I can't compare the one with curves against the ones that don't have curves. I somehow have got to compare people generally. My tool doesn't account for driver depth or LSF or dimming or optical conditions, and it's a work in progress. I'm getting in there probably about once a month and tweaking something on the back end to try and make it work a little bit better at the time. I really want you guys to shout out some numbers at me and we throw it into our calculator and see what happens. So that's this fun part of today. This is where I stop talking so much and I want to see you guys throw in some numbers. I don't have anything really other to talk about. I hope I've sort of given you my thoughts on maintenance factors. So someone shout out some numbers. I'm going to throw them into either the traditional moment or the LED moment to work on something. So
James, a couple of other questions.
yeah, go for it. Sorry, this is also part of the questions part of the day. So
Manufacturers quoting the C value.
yes, I have seen a couple of manufacturers quoting C value. The more variables we just with a formula solution, In my case, I just have to figure out how it affects the life of the luminaire, adjust a curve that goes with it, create a new formula, which is so much easier said than done, and we have a solution. Whereas a standard, every new variable we throw in there becomes a new table, which is an issue with representation of the data in the standard. So I'm hoping with the next issue of the standard, whenever that might be, we start to see a formula method to calculate luminaire maintenance factor, because tables aren't going to work for LED. They're going to work for every other source, and they've proven to work for every other source for a very long time. But for LED, it's just not going to cut it because they just vary too much. Much too much variation within LED.
What about driver life and performance, the way that it
Yes.
runs the legs?
Yes, so driver life and how it drives things, of course, as I mentioned, that doesn't factor into this either. A driver that fails early is or underruns the LED. So a driver that underruns the LED, you're going to get greater life out of the LED. Driver that just fails, that should be part of the LSF when we finally get there, when either I spend the time to figure it out or Standards Australia and their team spends the time to figure it out. And that will be interesting to watch that one develop over time as well, because drivers do die, and depending on the quality of the driver you buy, they'll die at different points as well, because we can all buy cheap drivers and we can all buy expensive drivers. And this is part of this market which is now so upheaved with all these additional inputs and how you take a holistic approach to assessing all the variables. So,
Have you got any comments on TM21 LED?
I don't specifically have any comments on, well, colour doesn't play into this too much, and the data from those standards or methods are approximates in that you run it for a number of hours and then you multiply it by the number you've 6 or 10 or whatever it was, and that sort of gives you your answer as far as an estimate of life. Estimating life is a bit rough, and everything we've got so far is estimates because no one's really run an LED for 100,000 hours, or manufacturers that have quoted at 150,000 hours or 200,000 hours, which have all been quoted by manufacturers. No one's run it for that long. They're just running it for a certain period of time and multiplying it, or taking a pure guesstimate to begin with, because there's plenty of guesstimates out there.
6,000 hours like that.
Yeah, 6,000 hours and then multiply it out, and that'll get you to the 50,000 hours.
Yeah.
You can multiply it by 10. And you know where you're at that point.
As a manufacturer, if we tested for 50,000 hours,
That's impressive.
by the end of that time,
The LED is redundant.
our luminaire is so old, everyone's got it in the museum.
Exactly it. Exactly it. LED market is moving, and it will continue to move. Even if it isn't a change to life, what comes forward, I reckon we'll see a change to simple colour performance more than anything else in the future of LED. I think we're all sick of CRI 80 on LEDs. I think we'll start to see things that push to CRI 90 as standard, and then we're going to leave that. We're going to start talking about TM30. Is it TM30? I'm looking for some nods. Yes, I'm seeing some nods. Yes.
Just a couple of comments.
Go for it.
In the new standard, it's interesting that it's the way it's designed using an incandescent.
Yes, it still does. I'm just going to go back to that old
band.
the standard table generally. There it is there without my comments. Yeah, they've really just added the one line and note 2 and note 3, because note 1 was the same. So that's been the big change. That was the big change in the standard. Everything else was just adding LED words here and there. Don't forget to include LED in your assessment or whatever it might be. So that's the 2017 standard, as simple as it comes. I don't know what to add other than that. You know, you've still got your, as Mick said, still got your incandescent, which we don't sell or own or use, can't sell.
Mercury vapors are off. You don't sell them.
Yeah, exactly.
Actually.
Mercury. It might be good to pull some of these out at some point, but you're not going to be using it anyway when you get to a 0.52 and a 0.5 for all the way down at 24,000 hours, when you can buy an LED that's much less. Maybe it's just a case of cleaning this up and just removing the stuff that isn't relevant. But it's
I could just make a couple of comments.
go for it, please, Phil.
With the incandescent mercury vapor still there, if you were doing a comparison on the lamp type.
Yeah, of course.
That information. And basically this table is an estimate.
Yes.
Where information is from and just to give a bit of history on LEDs, why there was no information at the time. Well, sorry, on the T8s, there's about 6 manufacturers.
Yep.
They all had the same deal.
Yeah.
We've now got LED lamp manufacturers.
LEDs, everyone's
10,000
different.
of them, 10,000 different ones, and there's no common value. So why those values are low and conservative values.
Yes, yes, and that's
if you want to go use someone else's manufacturers.
Yes.
Manufacturing, you ask them what they do.
I've certainly read this LED line as this is the bad LED. This is the one that
generic. That's a cheap and cheerful.
cheap and cheerful, nothing special LED. That's how I've read that line there. And if you want to get better than those numbers there, talk to the manufacturer, talk to the manufacturer, talk to the manufacturer. That's those 3 notes there reminding you to talk to the manufacturer if you want to get better than that. And certainly,
questions when you ask the manufacturer.
it's going to open a whole different can of worms. But that's what this standard intends to do, is saying, if you have no other data, use this one here. I'm trying to, through an internal tool, create better numbers than just that when the manufacturers are also missing data. And it is great to be able to compare back to older sources and see how they do in the scheme of running a lamp as well. When a client says, I've got this old fluorescent and it doesn't work too well, or halogen or incandescent, I've seen that recently. And it's in a plant room, it never gets turned on, and they're saying, do I need to replace it? I go, well, you do, but you don't. It's never getting turned on, so what's the point? If it's consuming no electricity off, as anything I replace it with is going to consume 0 electricity, it's all going to be off. So it's always considering how a client spends their money and runs their facility as well, because that, as I mentioned with the bathroom spot, if you know you're going to have a lower occupancy because of a motion detector, you can reduce your running hours, which is going to improve your maintenance factor, because you know on a realistic basis on how frequency on its frequency of operation. Correct. It's regardless of the source type. Yes. Although you probably don't want to be switching a high pressure sodium on and off 20 times in a bathroom. Yeah, not so much.
James, this process that you've got, method you use brings to life when you have an L9 B10 block fitting, and then someone brings in the contractor, and I'll send them to B50.
Yes. Yes.
And it's a 2000 lumen downlight, and you've got a 2000 lumen
Downlight. And
Same thing.
yep, exactly it. Alternatives is an interesting one, because that's certainly why part of the reason why I've developed this tool. Some of you may have read GHD's alternative text that I wrote, and it basically says no alternatives in about a whole page of text. It's really strict, and the reason for that is I wanted to fall back on the ability to compare A and B and say these two are not technically equivalent at any point. The 2000 lumens is, the L70B50 50,000 hours versus the L90B10 100,000 hours completely changes the thing. And then as a result, I'm happy to use the L70B50 50,000 hours. I need money to redesign, respace all the luminaires, bring them closer together. You're going to have to spend more capital, put it all in, put it together. You've got your installation costs, extra labour, all these additional things. That money that you think you're saving quickly starts to evaporate. Very quickly when you compare two different fittings.
Aesthetically, that may look similar.
Aesthetically, they may look similar. I've certainly seen fittings that look.
If you're looking at it before you switch it on.
Yeah, before you switch it on, yeah. No, I've seen some fittings recently that were identical to European fittings, and they weren't European fittings. And you compare the two, and you can see that they're completely different, even though they look exactly the same. You can tell straight away that this is a different quality product by that twist feel, that solder joints, that sort of thing. It's the sort of thing where there's no number I can ever attribute to how good it feels in my hand, but I can make up numbers till the car comes home, because that's what I've done really today. I've shown you how I've made up numbers, and I feel like I've done a better job of making up numbers than that line there, but that line there has a a reason for existing as well. So I'm trying to better and improve on the standard before the standard was released.
Just one last comment, James. All manufacturers
Oh, you do?
produce curves, but unfortunately they're curves from the chip manufacturer.
Yes.
And as you said before, once we put that chip inside the fitting, that's what changes.
I've seen Cree chips, the curves for them, and some of them have being an electronics manufacturer, what they do is they post things as an MTBF, mean time between failure, and they post numbers that are just bizarre, like 10 million hours.
Oh, yeah.
If you run it, or 10 or a million hours, and that's when you run it at a really low current. But the moment you actually start to use the chip, that degrades, and the other bit is they do have curves. But again, once you include for cooling and how they actually intend to run it, that changes as well. So there's plenty to consider there when it comes to how you get your data and if the data is correct. Always validate your data with a sanity check and what you're expecting to see. So.
When using occupancy sensors, switching cycles on an LED, impact adversely?
It won't affect the LED chip. It may affect the driver depending on the quality of the driver. So it's ultimately the LED chip prefers to be cold, and that's all the LED typically cares about. But the driver will notice transient spikes, will notice harmonics, will notice your power factor, all that electrical side of things, including your switching, that's affecting your driver. Once it's passed through a driver and all it's getting is a constant current or a constant voltage, the LED doesn't care as long as it's cold. That's about.
I've seen some figures that quote 100,000 switches or something.
Yeah, the basic structure of an LED shouldn't be affected by switching operations. Being a DC source, there's no point where you're switching at an uncomfortable angle, being a point on the sine wave, but that does happen at drivers, and you might switch at your zero crossing, you might be switching the top of your peak. That can affect your inrush currents and start tripping circuit breakers. That's one I've heard a lot of recently about LEDs, where switching them on at the top of your sine wave, and as a result, you get your inrush current and your circuit breaker goes ping. Any other questions? Any other comments? Anyone want to throw in some numbers?
I have a comment on the B value you're using.
Yes.
You're using that as a, so a B10 luminaire means that 10% of those luminaires have got down to that L90 or L70 value.
Yes.
Whereas a lot of manufacturers, the B value is a survival factor. So B10 of 100,000 hours means that 10% of those luminaires have failed.
Failed as in less than that value. Less than that value.
Okay.
Is what they mean it by. And so I've tried to represent that as much as possible on this chart, but you don't see it actually when you plug in that number there. You actually mostly see it in my chart based on the deaths. I assume that if 50% of the luminaires are below their stated value at L70, they're actually degrading faster than the ones that are only 10%. So I'm talking it as a degradation past its rated life figure, is how you see it on here, as well as it actually does affect the crossing point. The one thing that actually annoys me the most on this chart, and something I'm intending to fix, is the point that there is no rate at the crossing point. You'll see what I mean hopefully in a second, where I start to talk about rate of failure. Because a rate of failure is a number at any point in time. It doesn't suddenly change, it just... How many did they put there? That's too many. There we go, that's more reasonable. And let's say it's going to last 25,000 hours. Which really does make a difference. This point there, I'm not happy about that. I'm trying to smooth that out and get a more reasonable curve through there, because that what that implies is that at this point here, the LEDs suddenly start trying to die more frequently, is what that says to me, how I read that chart. And I have a problem with that. That's what I'm saying. My tool's not perfect, but it's a work in progress.
I actually think that's quite reasonable. The LEDs,
Oh,
typically, they don't have catastrophic failures, so the top part of the curve is quite good for LED.
yes.
But the curve for a driver life is quite different.
Oh,
So
yes.
flat,
Yes.
it
It's
takes
very,
off.
very much steepens off. Yes.
I think if you put those two together, you'll get something quite like that.
Oh, good. I'm glad the numbers look slightly reasonable. Because this is a whole luminaire result, not a just a chip or just a driver. So it is me trying to take into account the whole fitting rather than part of the fitting. Anyone else want to throw in some numbers as I'm inventing things as I go? Indirect is accounted for in full as well. That will kill your LMF and your RSMF. I love indirect lights. I use a lot of indirect lighting. It's a lot of good fun. But it does mean that your maintenance factor takes a massive hit as a result. I know, quite a high ceiling or something.
I don't actually see people going around cleaning their luminaires.
No.
So yearly intervals.
No.
Or even 3-yearly intervals.
Unfortunately, the standard only takes you to 3 years. That's as far as it goes. Beyond that, I'm fabricating data. This is a custom calculation method derived from 680.4. This red component and this purple component are directly from the standard. I'm not trying to change how the standard works. It would be inappropriate for me to do so. The only bit that I've really invented is that number there. So.
Have a look at the tables in the 1976 Australian standard.
If I've got it, we can find out if I. Well, let me. I wasn't born then. That's a good point. I wasn't born then. Let me see if I can go grab that, the 76 standard. See if I can find that quickly. I might actually stop the recording there because I don't want to go make a massive file and make this impossible to upload to YouTube or whatever it might be. But the plan is that IES across Australia and New Zealand is planning on making more recordings of technical meetings so that we can't make East Coast things sometimes and they can't make ours because we have such high quality presenters. And we'd like to share information. Yeah, if I do speak so myself, yeah. So we'd like to start sharing stuff between our chapters a lot more frequently. So hence the trial recording tonight, see how it goes. Hopefully it picked up my voice. Hopefully it picked up enough questions of yours and we'll give it a shot in the future. So I'll just stop that one there.